So we're talking about the fundamentals. We have the d electron configuration, we have oxidation states and nomenclature of coordination complexes. What is that? Well, that's not a piece of instruction, that is a recipe. That's how we're going to look at transition metal chemistry in terms of the fundamentals. So let's start with the d electron configuration. If you look at a neutral atom in a vacuum, now I cannot stress this point strongly enough. This is the electron configuration of a neutral atom in a vacuum. And the important point, in a chemical environment, as soon as you start doing chemistry and come out of that vacuum, the energy of the d level drops below the s level. And because they're lower in energy than the s orbitals, they are filled first. This is a really useful fact. It's really useful because it means that the electron configuration is reduced to simply the group number. So if you want to know how many d electrons your atom has in a chemical environment, then you simply take the group number. So in a chemical environment, the titanium atom will become 3d4 because titanium is in group 4, vanadium is in group 5, nickel is in group 10. And so when you're talking about transition metal ions, if I'm talking about a titanium 3 ion, titanium in oxidation state plus 3, how many d electrons will that species have? So if you want to know how many electrons a transition metal ion has, you simply take the group number and subtract the oxidation state. It's that simple. Don't even consider whether they're d electrons or s electrons. In chemistry, they are d electrons, and we just take the number of d electrons from the group number and subtract the oxidation state to give us the number of electrons in our species. And why is that important? It will tell us what the possible oxidation states are. So let's take titanium, for example. Titanium has the possible oxidation states of, well, if we're doing coordination chemistry, it could be titanium 0, which it will be then 3d4. It could be titanium 1, would be 3d3. It could be titanium 2, in which case it will be 3d2. Or it could be titanium 3, in which case it will be 3d1. Or titanium 4, in which case it will be 3d0. It cannot ever be titanium 5. You cannot have titanium 5 because you would have to remove 5 electrons, and that would require you to remove an inner electron. And that is never going to happen in chemistry. It might happen in a mass spectrometer or an ionization device in the gas, in the vacuum phase again, but in a chemical environment, you never ever have the oxidation state higher than the group number. So this group number, which is telling you how many d electrons you've got in your atom, is also telling you what the maximum oxidation state is. You can have any oxidation state up to the maximum oxidation state, but you cannot have an oxidation state higher than the maximum oxidation state. So the maximum oxidation state for titanium will be titanium 4. The maximum oxidation state for vanadium will be vanadium 5. The maximum oxidation state for chromium will be... Chromium is in group 6, and its maximum oxidation state is 6. Manganese in group 7, and its maximum oxidation state is 7. You don't actually find iron in oxidation state 8, but if you go underneath iron to ruthenium and osmium, you can find ruthenium and osmium in oxidation state 8. But clearly, you're removing all these electrons, it is becoming less likely that you're going to get these species.